Imagine that you are lying on a high hill on a calm summer night with no clouds in the sky at all. A gentle breeze carries the fresh scent of grass and wildflowers drifting around your nose. The sound of crickets chirping loudly mixes with the rustling of leaves in the trees, creating a background melody that feels like the music of the entire universe. Above your head, the deep black sky sparkles with millions of stars, but in reality, this is only a tiny fraction of the enormous picture that we are about to explore together. We will fly through space, feeling the icy coldness of the vast emptiness, hearing the imagined low hum of a spaceship engine, and letting our hearts tremble with the overwhelming immensity that makes human beings feel both humble and excitedly shaken to the core. Now, please join me on this journey, where every number is so large that it is hard to believe, but every detail is based on what scientists have carefully observed over many centuries. This starts from Galileo Galilei, who used a very basic telescope in the early 17th century to make groundbreaking discoveries about the heavens, all the way to the supercomputers of today that analyze data from satellites floating high above the Earth in orbit. These modern tools include powerful instruments like the European Space Agency's Planck spacecraft, which mapped the cosmic microwave background radiation in great detail. According to the latest estimates from the scientific community, which are constantly updated through missions such as the Planck Surveyor that finished its work in the year 2013, the Hubble Space Telescope that has captured millions of photographs since the 1990s, and especially the James Webb Space Telescope launched in the year 2021, which is now sending back images deeper into the cosmos than ever before, revealing galaxies forming. Just a few 100 million years after the Big Bang, the observable universe that humans can see stretches across a diameter of approximately 93 billion light-years. Let us pause for a moment to truly grasp this number. 1 light-year is the distance that light travels in 1 full year, moving at a speed of 300,000 kilometers every second, which means nearly 9,500 trillion kilometers in just 1 light-year alone. Multiply that by 93 billion times, and you will feel your mind spinning as if you are falling freely through space, with the wind whistling past your ears even though in reality the vacuum of space is completely silent. In other words, if we take the Earth as the central point, like a tiny speck of dust in the middle of the enormous Sahara Desert that covers vast areas of northern Africa, the limit of what we can see forms a gigantic sphere with a radius of about 46.5 billion light-years. Picture yourself standing right at the center of a cosmic stadium, but instead of seating stands filled with cheering crowds, there are billions of glittering galaxies all around, and the sound of encouragement is the absolute silence of space, broken only occasionally by the imagined distant boom of a supernova explosion in your mind. These supernovae are massive stars ending their lives in spectacular blasts, releasing energy equivalent to the output of an entire galaxy for a short time. Inside this enormous observable sphere, there are at least 2,000 billion galaxies hidden away, a figure estimated from deep surveys like the Hubble Ultra Deep Field completed in the year 2004, and further refined by the James Webb Space Telescope with its ability to peer through cosmic dust using infrared light, revealing even more small and faint galaxies that were previously hidden. Each galaxy is itself a massive collection containing hundreds of billions of stars, much like a city of light where the inhabitants are huge balls of fire. Among these stars, there are small ones similar to our own Sun, a yellow dwarf star that has been shining steadily for about 4.6 billion years, gigantic red stars that glow fiercely and produce enough heat to incinerate entire planetary systems, and supermassive black holes at the centers that swallow everything with terrifying gravitational pull. These black holes can have masses millions or even billions of times greater than the Sun, and they power active galactic nuclei that shine brighter than trillions of stars. Imagine that you are piloting a spaceship speeding through a spiral galaxy, with the engine vibrating softly, and in front of your eyes is the swirling arm filled with billions of stars twinkling like streetlights in a city at night. Occasionally, a nebula in shades of blue, pink, and purple appears like a living oil painting, where new stars are being born from clouds of gas with gentle explosions resembling cosmic fireworks. Nebulae such as the Orion Nebula, visible even to the naked eye from Earth on clear winter nights, are stellar nurseries spanning dozens of light years, filled with glowing hydrogen gas ionized by the ultraviolet light from young, hot stars. However, the true full picture of the universe extends far beyond those limits in a dizzying way. What we admire through telescopes, whether from high mountain observatories like Mauna Kea in Hawaii where the air is thin and freezing cold with the wind howling through massive telescope domes, or from space with the Hubble Space Telescope quietly orbiting the Earth at about 28,000 kilometers per hour, is only a small part of a much larger canvas and not the actual edge of the universe. Think of it as looking out the window of a small cozy house and seeing a pretty garden with flowers and a lawn, but beyond that lies endless fields, dense forests, vast oceans, and towering mountains stretching on forever without any visible end. Outside that 46.5 billion light-year radius, the universe continues to exist, spreading out infinitely in space that we cannot yet reach, like an ancient forest where sunlight has never penetrated the thick canopy, and the sound of falling leaves exists only in the imagination of future explorers equipped with advanced propulsion systems. The reason for this is simple, yet it makes you feel as if you are standing on the edge of an abyss in human understanding. Since the universe began about 13.8 billion years ago in the Big Bang event, which physicists recreate in computer simulations showing a tremendous explosion with deafening noise and blinding light, the light emitted from those distant regions has not had enough time to cross the immense distances and reach us here on Earth. Picture light as letters sent from the distant past, carrying images of a young, scorching hot universe thousands of degrees in temperature, filled with plasma and fundamental particles swirling in chaos, and we are opening each envelope one by one through our telescopes, with the faint sound of paper tearing in a dark laboratory filled with humming equipment. What is even more astonishing, causing scientists to cheer loudly in conference rooms with enthusiastic applause echoing off the walls, is that space itself is expanding continuously. This was first discovered by Edwin Hubble in the year 1929 through the redshift of galaxies, where light waves stretch to longer wavelengths as objects move away, and it is confirmed by the Hubble constant measuring the expansion rate at about 70 km per second per megaparsec, with newer data from the Gaia mission launched by the European Space Agency in 2013 providing even more precise refinements. This expansion is like the surface of a balloon being inflated with the soft stretching sound of rubber, causing the galaxies at the farthest edges to recede from us at speeds greater than the speed of light itself, a phenomenon that does not violate Einstein's theory of relativity because it is the fabric of space expanding rather than matter moving through space. Imagine standing in the middle of a large crowd at a festival, where everyone around you is gradually pulled farther away by an invisible force, with the sound of footsteps fading into the distance and eye contact becoming impossible. Therefore, even though those stars and galaxies are still shining brilliantly with life cycles spanning billions of years, potentially forming planets and perhaps even supporting life forms we can only dream about, their light may never cross the ever-widening expanse to reach human telescope lenses, leaving future astronomers feeling a deep regret like losing an old friend forever. Can you hear the sigh of the universe as those final rays of light fade away into nothingness? So what is the true boundary of the entire universe? This question has kept generations of scientists awake at their cluttered desks surrounded by scribbled formulas, with the scratching sound of pens on paper and cups of cold coffee sitting forgotten. From Albert Einstein with his wild hair and thoughtful eyes to Stephen Hawking, whose computer-synthesized voice delivered profound insights despite his physical challenges from motor neurone disease. And if we could somehow venture beyond that limit in an imaginary super-fast ship roaring through space with plasma engines hissing loudly, what awaits us on the other side? Perhaps unfamiliar galaxies with exotic matter, different physical laws governing reality, or just an endless repetition that overwhelms the senses completely. One of the most supported hypotheses by cosmologists, discussed in lively presentations at conferences like those of the American Astronomical Society with slides flashing on screens and excited voices filling the rooms, is that the universe is infinite. In this view, the universe has no borders at all, like a gigantic fabric stretching endlessly under silvery moonlight, with a smooth texture without any final fold or crease, no starting point and no ending place. And you can feel the freedom as you imagine running barefoot across it with soft grass tickling your feet. No matter how far you travel in any direction, even at speeds approaching the speed of light where time dilation effects make clocks run slower according to relativity, you will never reach an ultimate edge, only more space unfolding with the whisper of the vacuum. Simply put, the concept of a boundary does not exist in an infinite universe, much like the boundless ocean that ancient sailors feared falling off the edge of the world. According to one of the most popular hypotheses, supported by the cosmological principle that the universe is homogeneous on large scales, meaning it looks roughly the same everywhere when averaged over huge volumes, the universe could be an infinite space where galaxies in spiral, elliptical, and irregular shapes, nebulae like the Orion 1 with its sparkling star-forming clouds of gas and dust, and every celestial object we have ever observed occupy only a minuscule portion of the overall vastness, similar to a single grain of sand on an endless beach with waves crashing rhythmically. In such an infinite space, the uniformity and isotropy we observe, where the universe appears the same in all directions without a special center, is not surprising but inevitable, making you smile at the perfect harmony. Because in an infinite space, every single point can be considered the center of the universe, just like standing in the middle of the Sahara Desert where every direction is filled with golden sand and hot wind blowing steadily. However, there is another hypothesis that is equally convincing and widely accepted in modern physics through papers published in prestigious journals like Nature and Physical Review letters, backed by data from the cosmic microwave background radiation and galaxy surveys such as the Sloan Digital Sky Survey that has mapped millions of galaxies across large portions of the sky. The universe might have a finite volume but no boundary whatsoever, which sounds paradoxical at first, like a Zen riddle that invites you to sit in quiet contemplation under a tree. Yet this idea stems from Albert Einstein's general theory of relativity, published in the year 1915 with elegant equations written in white chalk on a blackboard covered in dust. Albert Einstein was a theoretical physicist born in the year 1879 in the town of Ulm in Germany, with a childhood full of curiosity about compasses and science books that sparked his lifelong passion for understanding the laws of nature. He is recognized as one of the greatest physicists of all time for revolutionizing our comprehension of space, time, and gravity. He developed the general theory of relativity, one of the two pillars of modern physics alongside quantum mechanics, where gravity is described as the curvature of spacetime caused by mass and energy. Although he is most famous for the equation E=mc², which relates energy and mass and is printed on countless t-shirts and coffee mugs around the world, he was awarded the Nobel Prize in Physics in the year 1921 for his contributions to theoretical physics and especially for discovering the law of the photoelectric effect, where light knocks electrons out of metals, paving the way for technologies like solar panels that convert sunlight into electricity and digital cameras that capture images using sensors. His work on the photoelectric effect was a breakthrough that helped birth quantum theory, even though he initially doubted its probabilistic nature and famously debated with Niels Bohr about the completeness of quantum mechanics. According to general relativity, the presence of matter and energy can bend the structure of spacetime, like placing a heavy bowling ball on a trampoline causing it to sag in the middle, and smaller objects roll along the curved paths with a gentle rolling sound. This allows the universe to be finite yet without any ending point, similar to the surface of a three-dimensional sphere where you cannot find an outer edge no matter how far you climb mountains or cross waters, you just circle around endlessly. To visualize this hypothesis more clearly, we can use an analogy by reducing the number of spatial dimensions, like playing a board game on a two-dimensional table. Imagine that we are creatures living in two-dimensional space, similar to characters in old video games with pixelated graphics, only able to move on the surface of a gigantic sphere that is smooth like a leather football under stadium lights. That surface is our entire universe, with no up or down, only directions within the plane we exist in, and the echo of footsteps on the curved expanse. We could travel in any direction forever without ever hitting a wall or boundary, just seeing the horizon curving ahead gently. But if we keep going straight for long enough with the patience of an explorer carrying maps and supplies, something strange happens. We return to our starting point, like sailing around the Earth and recognizing familiar faces approaching from behind with surprised shouts of joy. In this model, the universe is finite in size but has no endpoint, like a book where the last page connects seamlessly to the first. It is a closed space unto itself with no outside to escape into, similar to fish in a round glass bowl unaware of the world beyond the water with bubbles rising slowly. In our imagined two-dimensional universe, the total area is finite but there are absolutely no boundaries or edges, and the two-dimensional beings can live happily without worrying about falling off. Now expand that analogy to three-dimensional space, the world we inhabit with the laughter of children playing in parks on sunny afternoons and the warm smell of freshly baked bread in the morning air wafting from bakeries. Albert Einstein, along with other physicists like Georges Lemaitre, who first proposed the Big Bang theory in the 1920s as an expanding universe starting from a prime val atom, and Alexander Friedmann, who derived equations for an expanding universe in the early 1920s with solutions predicting different fates, suggested in handwritten letters and lectures with chalk squeaking on blackboards that our universe might work in a similar way. It is like the surface of a three-dimensional hypersphere curved in four-dimensional space, an abstract concept illustrated in computer models with vibrant colors swirling on screens. In this model, the universe could be finite in total volume, perhaps only a few 100 billion light-years in circumference if it were possible to measure around it, but without any ultimate end, like the globe of Earth but in a higher dimension. We as three-dimensional beings can only perceive space in the familiar three dimensions, with the height of skyscrapers piercing city skylines, the width of oceans stretching to distant horizons, and the depth of caves plunging into darkness underground, so we cannot detect or touch the hidden fourth dimension behind the structure, even though mathematicians describe it precisely with complex equations involving tensors and metrics. No matter how far we travel in the universe with next-generation spaceships like SpaceX's Starship currently undergoing test flights with roaring flames and thunderous liftoffs from launch pads in Texas, we will never find a final wall, only space continuing to curve smoothly. The boundary in this model simply does not exist, giving a sense of boundless freedom. If we could pilot a spaceship flying in a straight line forever through space, with crew members taking shifts to sleep and rest while air filters hum steadily in the background providing oxygen, it is quite possible that after a sufficiently long journey spanning unimaginable distances, the ship would return from the opposite direction, as if it had looped around the entire universe, and everyone on board would embrace in celebration as the theory is proven correct. Observations from the cosmic microwave background radiation, the leftover glow from when the universe was just 380,000 years old after the plasma cooled enough for light to travel freely, measured precisely by satellites like COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s with detailed temperature maps resembling a fingerprint of the cosmos showing tiny fluctuations that seeded galaxy formation, indicate that the space we live in is almost perfectly flat, with curvature less than 1 part in 1,000, like the surface of the Earth appearing flat on local scales even though it is a sphere. However, even a geometrically flat universe can have a closed topology, meaning it can wrap around itself without any boundaries, like the video game Pac-Man where exiting the right edge makes you appear on the left with the same maze continuing seamlessly. And then there is a bolder hypothesis powerful enough to shake our perception of reality, proposed by Alan Guth in the year 1981 and developed through eternal inflation theory, suggesting that our universe is not unique but just one among countless parallel universes existing in a vast multiverse as complex and diverse as the Amazon rainforest teeming with millions of species of plants, animals, and insects. This idea comes from inflation theory, indirectly confirmed through fluctuations in the cosmic microwave background and more recently through searches for primordial gravitational waves by experiments like BICEP located at the South Pole with sensitive detectors chilled to near absolute zero. According to this, right after the Big Bang in a fraction of a second smaller than 1/1000th of a billionth of a second, space underwent a phase of extremely rapid exponential expansion, swelling by a factor of billions upon billions of times at superluminal speeds, like a balloon inflated by a powerful air compressor with a whooshing sound. During this process, individual bubble universes could form independently from quantum fluctuations, each bubble a separate universe with its own physical laws, fundamental constants like the strength of gravity or the charge of the electron, and even different numbers of spatial dimensions completely unlike our own three-dimensional plus-time reality. In the eternal inflation model, the expansion of space does not happen uniformly or end at the same time everywhere but continues forever in some regions. While certain patches of space cool down and stop inflating, forming distinct universes with stable energy densities where stars and galaxies can form over billions of years, the surrounding space keeps expanding rapidly, generating new bubbles indefinitely like an unending process. Picture the whole thing like a pot of water boiling on a gas stove with flames licking the bottom and steam rising in clouds carrying the aroma of whatever is cooking. Bubbles constantly form and detach on the surface, growing larger before stabilizing or popping, each one an independent universe with its own set of natural rules, some where protons last forever without decaying, others where electrons are heavier than protons leading to different chemistry, and realities entirely alien with life perhaps based on silicon crystals rather than carbon chains. In this grand picture, our universe is merely one bubble floating in an infinite ocean of space, perhaps gently colliding with others through higher dimensions but imperceptible to us with current instruments. According to calculations by scientists using the lambda CDM model, where dark energy makes up about 70% of the universe's energy budget driving accelerated expansion, in roughly 100 billion years from now when dark energy dominates even more, the light from the last galaxies within our observable horizon will disappear beyond reach, assuming humanity still exists, perhaps having migrated to other star systems with advanced anti-aging technologies and intergenerational ships, traveling for centuries. By then, even with the most sophisticated telescopes as large as floating cities in space with mirrors kilometers across collecting faint photons, observers would see no galaxies at all beyond our own Milky Way with its few 100 billion familiar stars orbiting a central supermassive black hole named Sagittarius A star. The night sky would become eerily quiet, without the distant whisper of ancient photons traveling for billions of years, just profound darkness punctuated by a few nearby lights like lanterns hanging in the night at a remote campsite. Gone would be the glorious spirals of the Andromeda Galaxy, our closest large neighbor at 2.5 million light-years away, visible as a fuzzy patch to the naked eye on dark nights, and the sparkling star clusters like the Pleiades that adorn winter skies today with their blue-white glow from hot young stars. The entire observable universe would gradually shrink to an isolated region containing only the hundreds of billions of stars in the Milky Way quietly illuminating the void, with star birth and death cycles extending for trillions more years thanks to long-lived red dwarf stars that sip their hydrogen fuel slowly over tens of trillions of years. The universe itself would still exist, vast and continuing to expand forever in a heat-death scenario where entropy maximizes, but its magnificence would be forever hidden from inhabitants of the Milky Way, making them feel enclosed in a sealed snow globe shaken by no one. At that distant era, future astronomers, perhaps with biologically enhanced eyes or direct brain-computer interfaces linking thoughts to data streams, working in observatories with cooling fans whirring and screens glowing blue in the dim light, would face an insurmountable limit no matter how advanced their technology becomes. From their perspective, the universe would appear to consist of just one solitary galaxy drifting in endless emptiness, with cold brown dwarfs barely glowing and rogue planets wandering alone without stars. All traces of the grand past, from the redshift of distant galaxies measured in spectra with stretched emission lines indicating recession velocities, to the remnant cosmic microwave background radiation at 2.7 Kelvin filling space uniformly, would have faded completely as expansion dilutes photons to undetectable levels, stretching their wavelengths into radio waves too long to observe. In that world, they would never know that the universe once teemed with trillions of galaxies in superclusters like Laniakea, which includes our local group and spans hundreds of millions of light-years with gravitational flows mapping its structure. Today, we live in a golden age of cosmology, an era rich with data from ongoing surveys like DESI using spectrographs on telescopes in Arizona to measure baryon acoustic oscillations, Euclid Space Telescope mapping billions of galaxies in 3 dimensions, and the upcoming Vera Rubin Observatory in Chile with its 8.4-meter mirror and massive camera capturing time-lapse images of the sky to detect transient events. The sky remains brilliant with billions of galaxies visible through instruments, and gigantic telescopes like the extremely large telescope under construction in the Atacama Desert with a 39-meter primary mirror segmented into nearly 800 hexagonal pieces will gather the faintest light that has traveled billions of years across expanding space to reach Earth, carrying information about heavy elements forged in stellar furnaces and potential signatures of life in exoplanet atmospheres. From those ancient rays of light, humanity can trace back in time to see the early universe when the first atoms formed as the hot plasma cooled with a gradual drop in temperature, allowing electrons to bind with protons, and get closer to answering questions about our own origins, perhaps from a random quantum fluctuation in a pre-Big Bang state. But as spatial expansion continues with acceleration driven by dark energy confirmed through observations of Type Ia supernovae exploding consistently across cosmic distances and baryon acoustic oscillations in galaxy clustering, all distant galaxies will vanish from view, the cosmic horizon will contract inward, and the universe will grow cold and empty as if erasing its own history deliberately, leaving only lonely stars shining dimly and black holes evaporating slowly over Google years. Through Hawking radiation emitting particles quantum mechanically. We are fortunate to live in this moment, so lift your head to gaze at the stars on a clear night with the cool breeze brushing your skin and a profound sense of gratitude filling your heart, because the far future will hold only darkness and oblivion for cosmic observers. This long and detailed journey exploring the universe comes to a pause here. Thank you sincerely for your patient companionship through every image, sound, and emotion described, and I hope these vivid pictures, auditory impressions, and deep feelings remain in your mind forever like a bright and enduring star in the night sky.